The night sky has always felt like a gentle backdrop, thousands of twinkling lights that seem peaceful and uniform from our tiny vantage point on Earth. But here's the truth that hits like a cosmic gut punch. Those innocent dots are deceptive liars. Some are so monstrously vast that if you swapped one for our sun, it wouldn't just eclipse the inner planets, it would swallow Mercury, Venus, Earth, and Mars whole, with its outer layers stretching toward the asteroid belt or beyond. These aren't just big balls of gas, they're violent battlegrounds where gravity and nuclear fury wage an eternal war. Today, we're diving deep into the 5 largest stars ever discovered, building up to the current undisputed champion, a hypergiant so extreme that it challenges everything astronomers thought they knew about stellar limits. Well, we'll explore what makes these behemoths tick, why they're doomed to spectacular ends, and what their existence says about our place in an unimaginably vast universe. Stick around, because by the end you'll see the cosmos in a whole new, humbling light, and I'll leave you with a powerful takeaway that might just change how you view your own small problems. Let's start by demystifying what a star really is. Forget the simple image of a glowing orb. A star is a dynamic equilibrium, a constant tug of war. In its core, gravity crushes unimaginable amounts of matter with such intensity that atomic nuclei fuse together, releasing torrents of energy. This outward radiation pressure fights back against the inward pull of gravity, maintaining what's called hydrostatic equilibrium. It's this delicate yet ferocious balance that allows stars to shine for millions or billions of years. Disrupt it, and the star either blasts apart in a supernova or collapses into a black hole or neutron star. Our Sun, all for reference, fuses about 600 million tons of hydrogen into helium every second. It's been doing this for roughly 4.6 billion years and has several billion more to go. The surface we observe is the photosphere, where the energy finally escapes into space. Astronomers measure stellar sizes using the solar radius, our Sun's radius of about 696,000 kilometers, as the baseline. The giants we're discussing? They rack up numbers in the hundreds or even thousands. Their sheer scale warps our intuition. A light-speed photon that zips around the Sun in a few seconds would take hours to circle some of these monsters. Our journey begins with a star that's been hiding in plain sight for centuries, Cephei, often called the Garnet Star. Located in the constellation Cephei, this reddish beacon is visible to the naked eye on clear nights as a faint, deep crimson smudge. Discovered in its distinctive hue by William Herschel in the late 1700s, its color isn't just pretty, it's a telltale sign of its cooler surface temperature around 3,500 Kelvin, far chillier than our Sun's 5,800 Kelvin. As a red hypergiant, Cephei ranks among the most luminous stars in the Milky Way, visible without aid, pumping out energy at roughly 350,000 times the Sun's rate. Size estimates for Cephei hover between 1,000 and 1,500 solar radii, depending on the model and measurement refinements. Imagine plopping it in our solar system's center. Mercury, Venus, Earth, and Mars would vanish inside it, and its photosphere would extend near the asteroid belt between Mars and Jupiter. But size is only part of the drama. This star is shedding mass at an alarming rate. due to intense radiation pressure blasting away its outer layers. Hypergiants like this live fast and die young, while our Sun has a projected 10 billion-year lifespan. Cephei's violent phase will likely end in a mere few 100,000 years. When it finally goes supernova, the explosion could be one of the most powerful in our galactic neighborhood. At 2,400 to 2,800 light-years away, it poses no threat to Earth, but it will light up the night sky spectacularly. I often think about this when stargazing. That faint red dot up there is a ticking time bomb of cosmic proportions, a reminder that even eternal stars have expiration dates far shorter than we imagine on human timescales. To make this relatable, consider a real-life parallel from Earth. In 1987, astronomers witnessed supernova 1987A in the Large Magellanic Cloud, a blue supergiant that had been losing mass dramatically before exploding. The event provided a front-row seat to the death throes of a massive star, complete with rings of ejected material glowing for years afterward. Cephei's future could look similar, but on an even grander scale, with its ejected gas potentially forming intricate nebulae visible for centuries. It's like watching a massive oak tree in a forest, slowly shedding bark and branches before a thunderous fall. Except this tree, Cephei, could engulf our entire planetary neighborhood. Next up is a true celebrity of the skies. Antares, the bright red-orange heart of the constellation Scorpius. Ancient cultures noticed its rival-like glow compared to Mars, hence the name Antares, meaning rival of Mars. At about 550 light-years away, it's close enough for detailed study, yet its true nature remains awe-inspiring. Classified as a red supergiant, Antares measures around 700 solar radii, smaller than Cephei, but no less impressive. Its mass is about 12 solar masses, and it shines at roughly 100,000 times the Sun's luminosity. What sets Antares apart is its companionship. It has a smaller, hotter blue companion star, Antares B, orbiting at a vast distance of around 550 astronomical units. During rare alignments, astronomers have glimpsed this blue star peeking out from behind its massive red partner, a visual that underscores just how dominant the primary is, like a blue marble next to a crimson mountain. Antares, too, is in its twilight years, with loose outer layers being stripped away by stellar winds, creating a surrounding nebula of gas and dust. Its eventual supernova might briefly outshine the full moon, turning night into day for observers on Earth. Timing? It could be any moment in astronomical terms, tomorrow or in 100,000 years. Here's a vivid real-life example that brings this home. Think of Betelgeuse, another famous red supergiant in Orion, which dimmed dramatically in 2019 to 2020 due to a massive dust ejection event. The world watched in fascination as this star dimming made headlines, sparking speculation about an imminent supernova. It wasn't, but it highlighted how unstable these giants can be. Antares behaves similarly, pulsating and shedding material, reminding us that these stars aren't static, they're dynamic, evolving entities with weather on a stellar scale. If you've ever seen time-lapse photos of Betelgeuse's variability, picture Antares doing the same, but with an even more dramatic companion dance. Stepping further into the extreme, we encounter VY Canis Majoris, a star that once held the largest known title for years and still feels otherworldly. Situated about 3,900 light-years away in the constellation Canis Major, this red hypergiant is a chaotic outlier. Early measurements varied wildly due to distance uncertainties, but refined data pegs its radius at around 1,420 solar radii, enough to reach beyond Jupiter's orbit if placed at our Sun's position. What truly makes VY Canis Majoris stand out is its violent activity. Unlike many dying stars that eject material symmetrically, this one is erupting asymmetrically, forming a lumpy, irregular nebula with directional jets blasting from its photosphere. The surrounding cloud of gas and dust looks more like a turbulent storm than a neat shell. At one point, some astronomers even speculated it might be a binary system masquerading as a single oversized star, though that idea has been largely dismissed. It's almost certainly in its final life stages, and its supernova will be a fireworks display for the ages. For a relatable story, imagine the 1883 eruption of Krakatoa on Earth, a volcanic explosion so powerful it was heard thousands of miles away and altered global weather for years. VY Canis Majoris is like that, but on a stellar level. Its mass ejections create cosmic Krakatoas that reshape its immediate environment. Recent observations of similar hypergiants, like those in the Carina Nebula, show how these outbursts can sculpt beautiful yet destructive nebula, much like the homunculus nebula around Eta Carinae. These examples ground the abstract. The universe isn't just big, it's messy, explosive, and full of surprises that echo earthly cataclysms but at incomprehensible scales. For much of the 2000s and early 2010s, one name dominated largest star searches, UY Scuti. This pulsating red supergiant in the constellation Scutum was roughly 5,000 to 9,000 light-years away. Distances debated. Once claimed a radius of up to 1,700 solar radii. That would mean a diameter exceeding 2.3 billion kilometers light would take over 7 hours to circle it, compared to seconds for the Sun. Placed in our solar system, you'd have to venture between Jupiter and Saturn to escape its surface. UY Scuti's challenges include its location in the zone of avoidance, where galactic core dust and stars obscure views, plus its own 2-year pulsation cycle that makes size a moving target. The Gaia spacecraft's parallax measurements in 2018 revised its distance downward, shrinking the estimated radius to around 755 solar radii, still gigantic, but no longer the record holder. Debates continue because parallax at such distances has margins of error. Regardless, UY Scuti exemplifies how our understanding evolves with better tools. It pulses, expands, contracts, and reminds us that stellar sizes aren't fixed points, but snapshots in a star's turbulent life. A personal insight here. This revision process mirrors how science works in real life. Remember when Pluto was a planet? Or when we thought the universe was static? Each upgrade in technology, like Gaia's precise mapping, forces us to recalibrate. UY Scuti's demotion isn't a downgrade in wonder. It's a testament to human curiosity pushing boundaries. I've read accounts of amateur astronomers tracking variable stars like this with backyard telescopes, contributing data that refines professional models. It's empowering. You don't need a PhD to participate in uncovering cosmic truths. Everything so far has been building tension toward the current king, Stephenson 2-18, also known as ST 2-18, located about 19,000 light-years away in the same scutum region as UY Scuti. It resides in the massive open cluster RSGC2, Stephenson 2, a star-forming powerhouse packed with dozens of red supergiants. This cluster is already extraordinary, but ST2-18 eclipses its siblings. When first catalogued, its extreme luminosity made astronomers question if it even belonged to the group, perhaps a foreground interloper. Follow-up studies confirmed it's part of an outlying subgroup at a similar distance. Applying luminosity and temperature data to the stellar radius formula yielded a jaw-dropping 2,149 solar radii. That's roughly 1.5 billion kilometers, engulfing all planets out to Saturn's orbit, about 1.4 billion kilometers from the center. On its volume, around 10 billion times the Sun's. Luminosity reaches 440,000 times solar, pushing against theoretical upper limits for stable stars. Remarkably, ST2-18 may still be relatively young for a hypergiant and could swell even larger before its inevitable supernova, which might briefly outshine entire galaxies. Finding it buried in a dense cluster 19,000 light-years away, partially obscured, highlights how easily we could have missed it. In a galaxy of 100 to 400 billion stars, our maps are still crude sketches. To illustrate with a real-life story, consider the discovery of the pillars of creation in the Eagle Nebula. Hubble images revealed these towering gas structures, but later observations showed they're being eroded by nearby stars, dynamic and temporary on cosmic scales. Similarly, ST2-18's cluster environment is a bustling nursery where massive stars form, live briefly, and die explosively, sculpting the region like cosmic sculptors. And another parallel is the 2010s debate over the most massive stars in R136A1 in the Tarantula Nebula, which pushed mass and luminosity limits. These cases show how clusters like RSGC2 act as natural laboratories, revealing extremes we couldn't predict in isolation. One astronomer described spotting ST2-18 as finding a skyscraper in a forest of redwoods. It redefines big. Reflecting personally, these discoveries fill me with a mix of awe and perspective. In my own life, I've faced moments feeling small against big challenges. Career shifts, global events, personal losses. Yet learning about stars like ST2-18 reminds me that scale is relative. The universe operates on timelines where our entire civilization is a blink. Yet here we are, mapping these giants with satellites and math. It shifts my mindset. Instead of being overwhelmed by vastness, I find motivation in our ingenuity. We almost missed ST2-18 entirely, but sharpened tools revealed it. The same applies to personal growth. Deeper looks often uncover hidden strengths or opportunities. We've toured from the visible Garnet Star to this record-breaking hypergiant, each one more mind-bending than the last. What ties them together? Yet they're all in advanced evolutionary stages, fusing heavier elements, shedding mass, and racing toward dramatic finales. Their short lifespans, hundreds of thousands to a few million years, for hypergiants versus billions for sun-like stars underscore a cosmic irony. The biggest burn brightest but fastest. The key lesson or takeaway: embrace the humility and curiosity these stars inspire. The universe is far larger, stranger, and more dynamic than our daily worries suggest. Just as astronomers refine distances and sizes with better data, we can approach life's uncertainties with openness, revising assumptions, exploring deeper and finding wonder in the hidden giants around us. Whether it's a personal goal that seems unreachable or a global challenge that feels overwhelming, remember, tools and persistence reveal scales we never imagined. Don't fear the vastness. Let it fuel your next step. The cosmos isn't done surprising us, and neither are you.